In this tutorial, we are going to solve a question under work, energy and power. So here is the question for you. The frictionless system shown is released from rest after the light hand mass has risen 75 centimeters. The object of mass 0.5 m falls loosely from the system. What is the speed of the light hand mass when it returns to its original position? Okay, so now we have our diagram, as we can see. So what we have to understand is that they want us to find the original the speed of the light hand mass when it returns to its original position. So genuinely speaking, we know that the way the system is, we have two blocks which are on the left hand side and we have one on the right hand side. Okay, so they are saying that the one which is on the right hand side, it rises about 75 centimeters, which when we put this height, we can see that this h I'm going to put here to say my h is, I'm going to say 75. I have to change this into meters. Divided by 100 is 0.75 meters. Now what we have to understand again is they're saying that the mass which is on the right hand side, it went up, so it went somewhere there. Okay, so it was going up. We can see that this h, the one they are saying it was rises, is from there all the way to there, which we are going to call is just h. Now what we have to understand is that we are going to have the velocity. So I'm going to call let's call this one to be 1, this one to be 2, and then this one to be 3. Okay, so I'm going to call that velocity 3 initial. Okay, or I can say velocity at a. So I'm going just to say at this point I'm going to say it is the velocity at a, then this point is the velocity at b. So initially this system, it was going in this direction because the weight of the combination of 0.5 and 0.8, it was greater than the weight of the mass 3. Okay, the block 3. So now they are saying that after they are saying that after 0.5 mass was removed from the system started now going in this direction because the mass 3 had greater mass or had greater weight force now than the one for 0.8. That's the reason why it started going in opposite direction when that other mass was removed. Now before the mass was removed, this system was moving in this direction. Okay, so I'm going to say this is going to be shifted. If it's going in this direction, meaning we're going to assume that this m2 is going to come here all the way to this point. So this is our 2. Now it has started from this point all the way to this point. So now I'm going to call this one to be what? I'm going to call this one also, the h is the same. The height that m3 is going to use to rise is going to be the same as the height these two guys are going to fall. So the height is going to be the same. So I'm going to call also the velocity, this one to be VA, this one to be VB. Okay, at the same time what you have to understand is that even the m1 is going to fall from this point all the way to somewhere here. Okay, so it's going to fall from that point all the way to there, and we can see that it's going to fall from this point here all the way to this point. So I'm going to call the h is going, because it's going to fall with the same height, I'm going to call a. So this we're going to have also VA and VB. Okay, that is the information we have initially when it was going in this direction and not the opposite direction. We're going to come and analyze now the situation when it's going in the opposite direction. Now let's see. We have how many things? We have three. Okay, so we're going to say the mechanical energy initial has to be equal to the mechanical energy final. Okay, so I'm going to say the potential energy, I'll start with the one. Okay, the potential energy of A, okay, of 1, let me just put 1, plus I'm going to say the kinetic energy of 1, that is initially now, and then I'm going to say plus the potential energy of B, okay, let me say 2, plus the kinetic energy at 2, but we also have another one to the other side initially, so I'm going to have plus the potential energy of 3 plus the kinetic energy of 3. So this has to be equal to, we're going to have the same one, but this has to be just initial. So these are initial, this is going to be initial, also this one initial, this one has to be initial, this one has to be initial. This has to be equal to, in short, what I'm trying to say is that 1 is going to have potential energy and kinetic energy initially, 2 is going to have potential energy and kinetic energy initially, 3 is going to have potential energy and kinetic energy initially. This has to be equal to, we're going to have the same thing, but it's going to be the final now. So we're going to have the potential energy of 1, which is final, plus the kinetic energy of 1, which is final, plus the potential energy of 2, which is final, plus kinetic energy of 2 final, plus potential energy of 3 final, plus kinetic energy of 3 final. Now let's analyze. Initially, we know that the only we don't have any velocity. Okay, we don't have any velocity initially, so we don't expect to have kinetic energy. So initial, here on initial, we don't expect to have kinetic energy, so we are going to cancel kinetic energy because it started from rest where the kinetic energy is 0. So I'm going to cancel this. Okay, 2, the only guys which had the potential to fall is the 1 and 2. Okay, initially, because this was going up, so it was not falling. Okay, it was going up, so the only guys which had potential to fall is 1 and 2. So 1 and 2 we expect to have potential energy because they had ability to fall. Okay, so we don't expect to have potential energy of 3 initially. We don't expect to have this potential energy, so I'm going to cancel the potential energy of 3. Now initially we just expect to have the potential energy of 1, which is initially, plus the potential energy of 2 initially. This has to be equal to, let's now analyze final. Now final, what we have to understand is that these ones, they will come now to rest. Okay, the only guy which is going to have the potential to fall is the 3, the M3. So this is going to be on top here now, so it's going to have the ability to fall because it's going to have the height now. Okay, so we expect to have the potential energy quite okay for what we expect to have potential energy for M3, so this has to be there, but we don't expect to have potential energy of 1 because the H is going to be 0, so this is going to be cancelled. The potential energy of 2 is going to be cancelled as well because the H is going to be 0 at that point. Okay, when it reaches now down. Now let's analyze, let's now talk about the kinetic energy. When it has come down here, do we expect to have kinetic energy? Yes, because it was now moving, so expect to have, so we're going to have the potential energy of 3 plus we are going to expect to have the kinetic energy of everything now. Kinetic energy of 1 plus kinetic energy of 2 plus kinetic energy of 3, because now all these blocks were moving. Okay, now from here we can see that we can come up with the formulas. So it is m, the one, it is mg squared, but the mass, so let's just put mgh. Okay, then plus again here is going to be mgh. Okay, so now here we're talking about 1. Let's not forget, let me put m1 here, let me put also m2 here. So this is going to be, this one we're talking about m3gh plus the kinetic energy is going to be half. Now the mass is going to be m1. Okay, the mass 1. Then we have got the velocity. Now which velocity are we talking about? Okay, is it going to be the velocity b or the velocity a? Velocity a is going to be 0, or the velocity at a is going to be 0 because it started at rest, so we expect to have 0. That's the reason why we don't have anything. But now we need to find the velocity b, so I'm going to have the velocity at point b, so I'll square it plus half m2v b, I'll square it, then again plus half m3vb squared. Now let's analyze. We can see now from here that the m1 we have been told that m1 is 0.5. Okay, from here it's 0.5, so I'm going to say it's 0.5 m, okay, gh plus that one is 0.8 m gh has to be equal to this one. We have not been given, it's just m. Okay, so mgh, then plus half m1 is 0 times 0.5 m, then v b squared plus half m2 is times 0.8, which is m. We have to put m there. I'm going to have m, then v b squared plus half that m3 is just m v b squared. Now we can see m everywhere, we can cancel the m. Okay, so I'm going to cancel the m. Even here I'm going to cancel the m. Even here I can see m everywhere, so I'm going to cancel the m because I don't have mass. Now from here, now let's see what we have. Okay, we can see that we are going to have 0.5 gh plus 0.8 gh has to be equal to gh plus half. Then we're going to have times 0. Okay, let me just put this in brackets. So I'm going to have 0.5, then vb squared plus half, again 0.8 vb squared plus half m. Oh, we don't have m because we have cancelled the m. I'm going to have v b squared. Now from here, if I want, I can just simplify this and say I'm going to have 0.5 gh plus 0.8 gh is going to be equal to gh plus, I'm going to say 1 over 2. Okay, 1 over 2 is 0.5 times 0.5, so I'm getting 0.25 here. So 0.25 vb squared plus, then I'm going to have 0.5, which is 1 over 2 times 0.8, which is giving me 0.4 vb squared plus, then here we're going to have just 0.5 because 1 over 2 is 0.5 vb squared. Now we can get rid of everything here to create space. Now our goal is to find the velocity of b, meaning that now is going to be our initial velocity when we start now going in the opposite direction. Okay, Now we have our formula. This is our formula which we have just come up with. Let me put it here. We are saying it is 0.5 GH plus 0.8 GH to be equal to GH, the H is the same, plus 0.25 VB squared plus 0.4 VB squared plus 0.5 VB squared. Now let's see. I can now get rid of this, but remember that our H is 0.75 meters. Now we want to find the B, the um the VB. Okay, so what we're going to have now is I'm going to shift this part here to the left hand side. So I'm going to have 0.5 GH plus 0.8 GH minus GH to be equal to 0.25 VB squared plus 0.4 VB squared plus 0.5 VB squared. Now this part I'm going to factor out this side here. I'm going to factor out VB. Okay, so I'm going to factor out VB squared. So here I'm going to remain with the same 0.5 GH. Even here, if I want, I can factor out GH. Okay, so I'm going to say GH open bracket 0.5 plus 0.8. Then here I'm going to have minus 1. This has to be equal to, here I'm going to factor out VB squared open bracket 0.25 plus 0.4. Now from there I'm going to have plus also 0.5. So I can now add what I have there. Even here I can add. Okay, so the G, I can now plug in the values here first. I can say that, let me just say GH, in the brackets there I'm going to have 0.5 plus 0.8 plus or minus 1, 0.5 plus 0.8 minus 1, which is 0.3, meaning I have now 0.3 GH. Okay, I have 0.3 GH to be equal to, now I can also add what I have there, which is 0.25 plus 0.4 plus 0.5, which is giving me 1.15 VB squared. So I can divide both sides by 1.15, even here 1.15. So I'm going to have VB squared to be equal to 0.3 times G, which is 9.8, times the H is 0.75, then I divide it with 1.15. Okay, now let's see. So the VB squared is going to be, I have 0.3 times 9.8 times 0.75, so I'm getting 2.205. I divide this by 1.15. Okay, so what I'm getting here is I'm getting, if I do 0.3 times 9.8 then times 0.75, I divide it by 1.15, so I'm getting 1.91739. I'll leave it there. So if I want, I'll get the square root here to find the VB. So my VB, the velocity at B, is going to be, what is the square root of this? Is 1.38 46, which is the same as I just put 5 meters per second. So this was the velocity it was moving with when it was going down. Okay, so now we have to find the velocity when it was going up now. So now what we're going to do here is I'm going to put my velocity at B, hit this point, 1.385 meters per second. Then I'll get rid of everything here. Now what we have to remember now is that this was the velocity which was there at B. So now we are trying to find the velocity at A. So to find the velocity at A, what we have to remember is this. We have to remember to say this was removed. So if this was removed, meaning we no longer have this now. Okay? This was removed, meaning that this now, it started now going up. So this one was removed. We no longer have 0.5. Okay? So if that was removed, what we have to remember is it was going up now. 0.5 has been removed. Okay? So as you can see from the diagram, I've removed 0.5. That block was it has been removed. So now we want to see the velocity which we're going to have, the original velocity, when now it was going in this direction. So remember, initially we had this mass was somewhere here. Okay, then we had the velocity as our VB, then we had the velocity as our VA here. So when it was going in this direction, we took this as initial velocity and we said this is 0 because it was raised from rest. Now that that one has been removed, we can see that we had this mass. So we said from this point all the way to this point, it was what? Here we had A, VA, and then VB. Okay, and the H is the same. The H. Now, to find the velocity when now it changed the direction, it was moving in this direction, we're going to use the same. The mechanical energy initial has to be equal to the mechanical energy final. Okay. Now, initially, before it started moving, we have the initial velocity, which is going to be VB now when it is going in this direction. The initial velocity now we're going to have this VB and also this VB. So we expect to have potential energy and kinetic energy, but the potential energy which we're going to have is going to be the potential energy for last time I said this is 3 and this was 2 and the one which has been moved, it was 1. So since it is moving now in this direction, M3 had it was the only mass which had the height, so it had the ability to fall because this one was now down here. So we don't expect to have potential energy at that point. So initially we expect to have the potential energy of 3 plus the kinetic energy of 3, which is VB because we have found already, then plus the kinetic energy of 2 has to be equal to, now when it comes here, we expect to have the potential energy of 2 because 2 now is going to have the height, is going to have the ability to is going to have the potential to form. So we're going to have the potential energy at 2. Then we expect to have also kinetic energy because we want to find the VM at 2 and kinetic energy at 3. Okay. Now this one, the mass, we have been told that it is just m. So I'm going to say mgh plus the kinetic energy is half. What is the mass for 3? For 3 is just basically m. But this is initially, so it's going to be VB. This is going to be B, then squared. Okay. Plus, here is going to be, now the mass for 2 is 0.8. 0.8 m. Then I have VB squared. This has to be equal to the potential energy of 2 is 0.8 mgh plus this is going to be half. At 2 we expect to have 0.8 mva. We want to find va plus another one there, we're going to have half. The mass there for m3 is just m, then I'm going to have va squared. Now I can see that I have m everywhere. I can cancel the m. Okay, so to cancel the m here will go, this m will go, this m will go, this m will go, this m will go, as well as this m. So we're going to have gh, okay, plus this one is same as 0.5, 0.5, 1 over 2 is 0.5 vb squared, plus this one is going to be 0.5 times 0.5 times 0.8, which is going to be 0.4. So 0.4 vb squared I'm going to have equal to, I also have 0.8 gh plus, then there now I have also 0.5, which is 1 over 2 times 0.8. I'm having 0. I have 0.4, okay, va squared. So I'll get rid of this. I have 0.4 va squared plus we had 1 over, which is 3, so it's just m has gone, which is going to be 0.5 times va. Okay, so we're going to have 0.5 times va squared. Now from here we can see that this is going to give us gh plus 0.5 times 0.4 is 0.9 vb squared has to be equal to 0.8 gh plus that one is going to give us also 0.4 plus 0.5, which is going to be 0.9 va squared. Now I can shift this to the left hand side where I'm going to have gh minus 0.8 gh plus 0.9 vb squared has to be equal to 0.9 va squared. Now at this point I can get rid of this to create space. I can even move everything here. So I'm going to have this. So here is same as we have 1. So gh minus that one we expect to have 0.2 gh. Okay, because this is same as 1 gh. So 1 gh minus 0.8 is 0.2 gh. Then you have plus 0.9 times vb squared has to be equal to 0.9 va squared. Remember we have our vb already. We want to find the va. That is going to be the original the speed when it went to the original position. So I'm going to have 0.2 times 9.8, the h is 0.75, then plus 0.9, the velocity is 1.385 squared has to be equal to 0.9 va squared. Okay, now from here we are going to say 0.2 times 9.8 times 0.75, so this is giving me 1.47. Then we also have 1.385, I square it, times 0.9, so I'm getting 1.72. So this one I do plus 1.47, so I'm getting 3 so if I do plus direct here, I'm getting 3 I do this plus this, I'm getting 3.196. This has to be equal to 0.9 va squared. Now at this point I can divide both sides by 0.9, even here by 0.9, meaning my va squared is going to be, if I divide this by 0.9, I'm getting 3.551555. Okay, so I have to get the square root both sides. So I get the square root, my VA has to be equal to 1.88. I'm getting my VA to be 1.88 meters per second. So this is the answer for this question.